modeling a little bit more seriously, more thoroughly. So one of the books that people use the most nowadays is Modeling Infectious Diseases in Humans and Animals. And the authors are Matt Keeling and Pesh Rouhani. So that's a kind of textbook. It has from the very basic facts to many other discussions, spatial dynamics, stochastic dynamics, everything. And then there's also a nice book, which is a book of chapters. Each chapter is written by one scientist, which is the Mathematical Epidemiology. It's more mathematical than the other book, and was edited by Fred Bauer. And others. Pauline van der Driesch in Wu. And so I will leave this here at the end of the class. If you want to just take a look at the contents, you're welcome. So let's start with the very basics. So the first basic thing is that we will, yeah. Yeah, it is working, but yeah. But can you hear, or is it because this can be set? There's a setup from. Okay, I think. So first of all, that's maybe a trivial thing for everybody who is here. We are talking about infectious diseases, transmittable diseases. It is not so obvious for some people that if, for instance, if you go to the Department of Epidemiology in a public health school, and at least half of them do not work with epidemics of infectious diseases. People will be working with cancer, with obesity, and it's not transmittable, but somehow take it epidemiology to also say it's also about non-transmissible. So we are talking about transmissible diseases. And second, well, there are several ways that a disease can be transmitted. So essentially, there are directly transmitted diseases, and that are the most very common things, like all respiratory diseases, sexually transmitted diseases, also even if they are not respiratory, because respiratory means it's a symptom, airborne in general, and also directly transmitted. And also there are diseases that are transmitted by the body fluids. Right? So this was the case, for instance, of smallpox. It is eradicated. And when I talk about indirectly transmitted diseases, this is usually meant to be what people say vector-borne. It's transmitted by mosquitoes like malaria, dengue, or by ticks also. Or also, which is not a vector, but it's similar, is waterborne diseases like cholera. So that there's not a vector, but there's a part of the transmission goes through an environmental factor, which is, in this case, water. So these are essentially the context we are working. And also, the first step, we will now look for models, which will be, there's some overlap with Joshua, anyhow. But we will look for models where the population considered is constant. Right? So when is this okay? Right? Or why is this okay most of the time? Because population change in the population goes relatively slow. Most of, not all, but many of the diseases that we will be interested, if you look for the epidemic, right, they will be over some months or 1 or 2 years. And over this time scale, the population probably did not change very much, unless, obviously, unless you have very deadly situation or something. But the population, the normal demographics of the population goes on a very long time scale with respect to the disease time scale. So we will take all the time the population to be constant. Well, so the first thing we will be talking about compartmental models. And I will discuss what the SIR model in a little bit more detail. So the idea is that every individual in a population, on the focused population, is classified either as susceptible, infected, or recovered. Right? So recovered means, for our purpose here, will be immune. Right? And also for the purposes here, the infected is the same as the infective. Okay, so we are not distinguishing. There could be, and I will comment on this, people that get infected but only transmit later. Okay, so in the SIR model, we do not make this distinction. So we have only SI. So you have S, you have I, you have R. Usually you draw it like this. S becomes I, then this goes to R, and usually you put a set like this, saying that S in contact with I can give you a transition from S to I. Okay? So, and you want to build the most elementary mathematical model for this kind of situation, which will be the model which is called the SIR model, that gives you the rate of change of the number of people in these classes. Okay? So S, therefore S is the number of people that are susceptible, I is the number of people that are infected, and R, so this is the number of people that are recovered, and I will suppose that S plus I plus R is equal to some N, which is a constant. It's not depending on time. Okay? So the way to do this is usually the following. If this is a disease where people get recovered and get immune, the susceptibles can only decrease. Right? So let's put it something like this. It's proportional to S with some lambda. Proportionality constant, and then you say, oh, everybody that gets infected gets out of the susceptible goes here, and then the infected will also go out of the class of infected at a certain rate, which will be mu, and enter here. Okay? So if you add this equation plus this equation plus this equation, you get that ds, the derivative of S plus I plus R is 0, because everything cancels on the right-hand side, and it's equal to N. Okay? So let us proceed very slowly, actually, and let us discuss what these terms mean. So first, let us take a look at mu, this guy. What is this guy? So forget about not look at this equation, but forget about this first term. So when you write di dt, somehow proportional to minus mu I. Right? If you look only at this process, the process of getting out of the class of infected and going to the class of recovered, then so that means that individuals leave the class of infected at a rate mu. Now, we want to make sense of this mu, and a way to look at this is the following. Consider what we would call a cohort of people, a certain number of individuals that got infected at the same time. Okay? They got infected at the same time. Well, if they leave the infected class at rate mu, then obviously then you will have this equal in this case. Okay? And so the time the infective, the number of people infected after a certain time, say S, okay, will be I of S divided by I of times 0, the time where you get the people who were infected. This will be equal to e to minus mu times the time S. Okay? So that the length of the infective period can be thought as being distributed as an decaying exponential. Okay? So, and if this is the length is distributed as a decayed exponential, the average time will be given by something like this integral to e to minus mu s gs from 0 to infinity. So this is the mean time, which will be equal to 1 over mu. Okay? Therefore, 1 over mu is the mean time that an individual stays in the infective class. Okay? 1 over mu. Okay? Therefore, this is the 1 over the infected period. Why is this important? Because here we start to make connection but with things that can be measured or estimated somehow. And this is one thing you know that, for instance, for certain diseases like flu, this has to be something like 1 over mu should be something like 3, 4, 5 days. It's not a month, it's not a second. So you already have the order of magnitude of this parameter. Okay? It's just different if I didn't have this interpretation and I have data and I want to fit the model. If I would fit the model with this guy here, I would have one more parameter to fit and could be, say, completely wrong in the sense that it could give you a recovery time that is anything, right? So, okay, that's the term, which is the term that says how are you flowing out of the infective class. Now, let's take a look at the other ones. This lambda here has a name, it's a jargon in the air, it's the force of infection. And what you expect is that lambda should depend on the number of infectives. If more infectives are present, then you expect that the force of infection, which will determine the rate here of this dsdt, there should be a stronger force of infection. So somehow lambda has to be proportional to I. And we will take lambda, I will use this beta I over n. Now, with this, so I will discuss why you have this n here, but before I do that, let me just write down the SIR model for completeness. So, well, why is there an n here? This guy. Does anybody know this answer? You have an idea why you need this n here? No idea? Yeah, n here. A little bit louder, I can. It's the proportion of infected. Yeah, it's more or less on this line. So the point is that this, for most of the diseases that we study, say, let's think about COVID. Okay, we are here in São Paulo with more than 10 million people. Now go to the next big city here, it's Campinas, with roughly 1 million people. So a factor 10. Are the epidemics very different in Campinas and in São Paulo? No. Okay? So what they will be different by a scaling factor, but if you look at the epidemic curves, they will be similar. The time it takes to end the epidemic and the times to come to a peak and so on, all of this will be similar. Therefore, you don't expect that your equations that describe your epidemic model, they should depend only on the fractions of susceptibles and the fraction of infectives and the fractions of recovered. So if you look for this here, and now you write down, you define small s is capital S over n, the same for the other variables. And then if you substitute this here, right, like this here, into the equations, okay, then you see there will be a small n here times n, because you substitute s like small n times n, everything here, and then you will have an n here, an n squared here, an n here, an n here, n squared, but you have an n here, makes it linear in n, and then there's another one here that cancels, and therefore you will get an equation that is just like this. Which depends only on the fractions, okay? Does not depend anymore on, it does not depend on n anymore, okay? So introducing this n, if you didn't have this here, you would not have this n here. And then you would have an n squared coming from the substitutions of capital S and capital I. And then you would have one n here and another n square here. You would cancel them. You would have a factor n. It would say that epidemics in cities of different sizes would be completely different. The rates of increase of I, for instance, would be scaled by n. And that is just not true, okay, in general. Not in general, in most cases. So introducing this way, now the equations can be seen to be only what people call frequency dependent or fraction dependent. Okay? Now I want you to speculate with me. Why should this be true? Why? What is the mechanisms that makes this thing happen? Why is an epidemic here in São Paulo and in Campinas essentially has the same growth rates and everything? Why? No, I think it's more simple than that, actually. Yeah.
Social groups are of the same size.
Hmm?
The social groups of people, the number of people that you interact in your daily life will be almost the same.
So, okay, so what he's saying is that the social groups, the people that you meet, the number of people that you meet, is more or less the same here in São Paulo and in Campinas. Okay? And that's actually, it is true. What happens is that you don't expect big differences between cities of like 1 million, 10 million, because the number of interactions, which can be possibly infective, say meeting or sexually transmitted diseases and so on, which depends on the number of possibly transmission encounters, is not very different from one city to the other. Therefore, the epidemics should have more or less the same aspects. Okay? So, therefore, this is a result of the structure of contacts in the human society. And there's a... There could be... Yeah, that yeah, culture, that's... concentration of people, yeah. So, the different sizes of the cities can matter mainly, but what is more important is if you are studying a population in the urban area or a rural area. In the rural area, the number of contacts is far smaller. Okay, so we will discuss the R0 for some of the diseases, and for instance, for measles, R0 is like 14 in the cities, but it's only like 6 or 7 in rural areas. Okay, so this is one thing. There is an importance of the network structure of the contacts, but this depends on the particular disease, because I will discuss in a moment, because you have to define contact, which is not so obvious. Okay? So, good. So what was I doing now? Okay, so let's discuss population size. Okay? So we are talking about N here. Okay? So what are we referring to as the population size? Okay? So is this always, say, if you want, for instance, to model a disease in a country? I remember seeing things about Zika virus in Colombia, for instance. And do you have to take always the population of the country as n? Why not? Or why yes? What's the population I should take? So if I do Zika virus epidemic in Colombia, do I take the population as being the population of Colombia?
Maybe conditions of different people from different zones of that country could be very different. So you are reacting very heterogeneous conditions. So it depends on which grade of detail you want.
Yeah. So, for instance, there could be in a country like, for instance, Colombia, but it also would be the case of Brazil, you have several climates, and maybe the disease that you are studying, it's a vector-borne disease, and maybe there's the vector does not survive in a big part of the country. Therefore, the population that lives in that part of the country is not exposed to any contact, okay? So what you need is always to make a sensible choice of population when you model, in the sense that, for instance, my group here in São Paulo, we have modeled a lot of things with COVID-19. We never made a model for Brazil, because you can have an epidemic going on in the northeastern part and nothing happening in the south. There's so much heterogeneity, and then you will just take as all of this as one population. And then, so it is not in this case. So it is much more reasonable that your spatial scale and corresponding scale of the population size be sufficiently homogeneous in terms of transmission rates and so on. Okay? This is also important when you think about, for instance, dengue. We know that dengue has very different transmission dynamics and incidences in regions like, for instance, Rio de Janeiro has a lot of dengue. If you go to the south, Porto Alegre, there's almost nothing, although it's now increasing. But okay, so a model which should take large part of Brazil and consider this model and the total population of a big area would probably not be very good. Okay? So it makes much more sense to take a model for city of Rio de Janeiro. And then obviously we have also heterogeneities because there are places where are more likely to find the mosquitoes and so on, but at least that population size makes some sense because they are all exposed potentially to the same pathogen. Okay? So that's the first thing. The population size is important that it is chosen to be something that's meaningful. Okay? Now, coming back to this frequency dependence in the SIR model. Okay? So surely we should have that somehow the number of possible transmission contacts should somehow be present in this model. And the only way to be present in this model is to be in the beta, okay? So, but when I say possible transmission contacts that could have an infection, then there's a point. What is a contact? What is a contact? Are we all in contact? Or not? Depends on the nature of the infection and the nature of the transmission dynamics. So contact is best defined with sexually transmitted diseases, obviously. That's a case which is clear. But for respiratory, airborne diseases, that can be quite tricky, okay? So it's not obvious that we are potentially, all of us, are we in contact? Or do I define a contact only if I have a, say, if I talk to a person during a certain number of minutes, and then, so what is contact in this context? Can be pretty much complicated to study, okay? So, okay. So these are more things that I think you should pay attention when you do the modeling, because we have seen over the last years, lots of people making confusion with this. Now, before I go for my next step, let me mention here, you have this nice model, and you can imagine that there can be extensions of the models with asymptomatic or diseased people and so on, and we can discuss this a little bit at the end. But here you have 3 variables, S, I, and R. Okay? So, say it's like COVID. Which of these variables can you measure from epidemiological data? Beta, no. Beta is difficult. Which of the is S, I, or R? Which one? I. You think it's I. So I, what is I? Yeah, okay, you have.
You can be sure with coverage because you can detect antibodies.
Mm-hmm.
So maybe you can, you know that person has
Had contact.
disease and they develop it. And also you have to take into account what kinds of antibodies to know how much time is passed.
Okay.
They got those antibodies.
Mm-hmm. Yeah, so more ideas of which of the variables, and with arguments, which of the variables are measurable, observable, if you want.
Infected is harder because maybe you can detect.
So, actually, yeah. Okay, that would be an idea, but this is not measuring this. This is estimating, okay? Mu, yeah, but mu is not a variable. I mean, S, I, and R are the variables. Mu is a parameter, yeah. Of susceptibles. So actually, more ideas? No. No. None? You can't, in most of the situation, you can't measure neither S, nor I, nor R. Okay? Unless, for instance, the case you made for R, if you had an epidemic that confers immunity, lasting immunity, and the epidemic is over, and then you do a serological survey, but you would have to test all the population. Okay, so it is in principle observable, but in practice it won't be, because people don't want to be tested if they don't have any disease. Okay, so that would be a problem. But if you have an epidemic that's ongoing, right, you don't know neither S nor I nor R, because I is the number of active infections. How would you know this? Right? So what you know most of the time is the number of new cases per, say, day or per week. Right? The number of new cases. And usually, it depends. For instance, for COVID, what you can know, for instance, with Brazilian data for COVID, what you can get is the number of new cases per day of people that get hospitalized, because this generates an immediate notification process. And then this is something that you can measure. I will discuss these aspects of COVID in my second lecture, because there are problems with delays in notifications and so on. We will talk about this later. Okay? So, in principle, the best thing you can hope for in most modeling exercise is that you know the number of new infections per day, which is essentially this guy. Beta Si over n. This is the number of new infections, okay, per day. Right? So you can get S times I times beta divided by n, which, you see, this will pose a big, big problem, actually. Most of the time, if you have a more complicated model, but full of parameters. Here we have only two parameters. Right? We have mu, which you can estimate by knowing the typical time the disease is, the effective period. Beta is always a fitting parameter. You have data and you have models, and you want to make a fitting. Usually beta is fitted. Okay? So it's not something that you know mechanistically. It's just a fitting, statistical way of getting. But if you do have others, things that you might know, but then you have to modify your models. For instance, the number of people that die of the disease per day or per week. This is something usually known. But then you have to have a new compartment with people that have diseases. The same thing is, it's easier to know the number of hospitalizations due to a certain disease. But this means that you have to modify your model to include a new compartment where you have the compartment of people that are infective but have been admitted to a hospital, and the people that are infected but they have milder symptoms and they are not at the hospital, but maybe then this guy you can know. And then you take all your model and you use this data to fit the model to your and find the parameters that. Okay. So, okay, let's go for the next concept. The next concept is R0, what Joshua already talked about. I will go a little bit quick with this. So, this guy here, I will use this notation here for R0 or R0. I use this because not to make confusion with the R, which I wrote the R here, has nothing to do with this guy. Okay, and so, well, we have this SIR model where you say, I want to solve it, but instead of solving the SIR model, which can be done computationally, we want to answer a question. Given a population which is entirely susceptible at the beginning, and if I introduce a small number of infectives, will there be an epidemic or not? And definition for us of will there be an epidemic or not, it's a more mathematical thing. It's the number of infected will increase. Right? In a real situation, you have usually several introductions, okay? Because you have stochastic dynamics with small numbers. But for our needs, we will say that, that an epidemic happens if a small fraction of infected is introduced in a completely susceptible population, and if the number of infected increases, then you have an epidemic. And therefore, it's very easy to find the conditions to have an epidemic if you look to this equation for I, which will be beta Si over n minus mu I. And that's essentially what Joshua made. So at the beginning, S is equal to approximately equal to n, everybody. Okay? So gi dt in this case becomes a linear equation, okay? Because S over n is constant. And therefore, if beta bigger than mu, we have an epidemic, or in a more common way, beta over mu. This means epidemic. Okay? So that's the condition for in the SIR model for an epidemic to happen. And this situation here is good if you have a population that is actually susceptible. And this is most of the time, this is applicable for new pathogens. Everybody is susceptible, like COVID-19, right? So everybody is in principle susceptible. But pay attention that sometimes you don't have occurrence of a disease in a population, but actually you have people that had contact in the past with the disease, and therefore your initial population is, your initial size of susceptible class is not necessarily it's not necessarily n, could be smaller than n. So say that you have immunity in the population. So they're immune people. How can there be immune people? If the disease confers immunity, if you had it, or if have been vaccinated in a case where the disease has a vaccine. So then at the beginning, S is not only not n, but we will introduce some individuals that I will call V, which are the immune guys, okay? So the immune guys plus S is everything you have at the beginning, okay? So then I go back to this equation, and we have a small modification of it. You have di dt, and let's calculate this at t equal to 0, okay? Will be beta, and now instead of S, you will have n minus v divided by n I minus mu I, which gives you, let's write this a little bit better, 1 v over I, and 1 minus v over I. And if you want to find the threshold value, well, okay, this is just this, beta. And if this here is bigger than 1, then you have an epidemic. If it's smaller, you don't have an epidemic. Okay? So this condition, if you now divide everything by mu here, you will have that R0 times 1 minus V over N bigger than 1 epidemic. So this can be thought as the very simple model for herd immunity and vaccination. So say that all immunity that you have in the population is due to vaccination, then you look at this here, and you want that this product here be smaller than 1, so that you don't have an epidemic. Well, if you want this thing to be smaller, you can increase V over N, which makes the product here smaller. So if you have that V, why did I write this in? Okay. If you have V over N, this, bigger than 1 minus 1 over R0, then you don't have an epidemic. Right? So this says a lot about what is the kind of coverage that you need for a disease, for the vaccination for a disease, in order to have the population, which in ecological terms we would say not be invaded by a pathogen. Right? So let me see if I have a list of values. Yeah, I have a list of values of R0. First of all depends only on R0, okay? So just have an idea, smallpox that has been eradicated had an R0 typically of 6, which means that the vaccine coverage would be 83%. However, there's still a point here. No vaccine is 100% efficient. So you should also take into account the efficiency of the vaccine, which could give you some factor in front of the V, okay? So I'm not taking this into account, but in practice you have to do this. For instance, for measles, in urban settings, it's typically 16 R0. You need a coverage of 94%. Measles vaccine is highly efficient. It's like 98%, something like that, with 2 doses. But still, this means that you will have to vaccinate 97% of your population, not 94% of your population, to attain herd immunity, which is, in most of the cases, will be nearly impossible. Right? Nearly impossible. Okay? There are always people that are, for instance, you have newborns, they cannot be vaccinated before 1 year of age. So depending on your demographics, that could be a portion sufficiently big. But, well, then there are other things also, behavioral things. So, for instance, COVID-19 initially was like 2.5, would mean a coverage of 60%. And Mpox was estimated to be 2, R0, 50% coverage you need. And recently we have seen the resurgence of epidemics of cholera. And for instance, cholera in Zimbabwe had been estimated an R0 of 2.7, which means 62% of coverage needed to have herd immunity. Okay. Good. Well, any questions about that? So, now, with COVID-19, we had a lot of confusions about the concept of herd immunity. Right? So, at May or June of 2020, people were exultant saying, oh, we are at herd immunity, we can reopen everything. It's gone. Okay? And as Joshua already discussed this, that's not true, because there is something called overshooting. Okay? And where does this confusion come from? The confusion comes from the fact that if you look at this equation, this will have a solution, for instance, like this for I. Let's say the solution for I and time is something that does something like that, and then you have a peak. Okay? And when does this peak happen? This peak happens when di dt is equal to 0, okay? Which means that S over n has to be 1 over R0, okay? From this equation here, I cancel the I put this equal to 0, then you have mu over beta, S over n is equal to mu over beta, which is 1 over R naught. And therefore, the total number of infected people, so S is equal to n minus I minus R, okay? And if you put this here, you will have 1 minus I over I plus R over n is equal to 1 over R0. And what is this? I plus R is everybody that has been infected, okay? The people that are infectious now, plus the recovered. That's the total size of the population that has been infected. That's the number of infections. Therefore, the number of infections at the peak, I will use this, is exactly what? 1 minus 1 over R0. Which happens to be the same expression as here. Okay? Therefore, this generated this whole confusion about herd immunity. So this, when the total number of infections attain this value, you are at the peak. But when you go down this way, you still have infections. Okay? And there's the famous overshooting. Okay? Moreover, you don't know number of active infections. You know the number of new cases per unit time. And the epidemic curve for I and for the incidence, which is the number of new cases per day or per week, the epidemic curves are not the same. And they have peaks at different points. So if you look for the epidemic curve of number of new cases, it will be similar to this, but the peak is before. Okay? That's not difficult to, I won't do the calculations because it's a little bit technical, but if you look at the new cases and you say, oh, we are decreasing now, doesn't even mean that you have at the peak of I. Okay? So that is important to note. Wow. More. Now, we have been told that R naught is the number of new cases that are infected persons generates over the course of the infection. So why is this definition, this verbal definition, the same as here? So the same means the following. The number of new infections that one infected individual will generate should be something which is proportional to what? So now I want you to give an input. You take a typical person from a population, he got infected. How many will he infect? On what variables, on what parameters does it depend? Number of potentially infectious contacts, okay? More. Yeah?
How much virus they have?
Viral load. Could depend on that. Okay.
The amount of viral in the
Okay. That could be more. period of infection. If you stay infectious for one day, it's different if you stay infectious for a whole week. Okay? So this somehow should depend on, I will use this notation for number, the average number of contacts. And this has to be multiplied by something else, which is the probability that a contact is actually a susceptible guy. And if you say that everything is well mixed, this is just S over N. Okay? So then it would be S over N. Then it should be proportional to the probability, let's say gamma, the probability that, given that you have a contact, given that this contact is susceptible, what's the probability that it actually generates an infection? Because this is our probabilistic processes. It is not that all contacts will generate infections. So there's a probability that this will generate infection times the duration of the infection. Right? So if you look at this, then if you say S is close to N at the beginning of the infection, and if you say I will take K times gamma as a new constant, which I call beta, then you will have that this here would be T times beta, but T is 1 over mu, okay, which is beta over mu, which is actually the R0, R0 that we calculated from the model. But here you see that there is a definition which is not dependent on the model, which turned out to be the same, but the definition is not dependent on the model. Right? I don't think I will have time for what I will in this discussion, but it is possible to calculate R naught, or even what people call R of t. R of t would be when S is not necessarily close to N, then you would have, I would say RT would be the R0 times the S over N. Okay? That would be the effective reproduction number at a certain point of the epidemic, not at the beginning. Okay? And in the same way as we can understand R naught without even talking about SIR model here, it is also possible to calculate R naught or RT without writing down a whole model. And this is done with something which is called renewal equation for the incidence. But okay, if you want, I can give you references, and that's it's a method that is pretty much used because it has less hypothesis about the dynamics of the epidemic than a model. Well, okay. Now, we can get also something which is very interesting from the SIR model without solving any equation, which is to obtain the equation for the final size of the epidemic. So what's the final size of an epidemic? If we have an epidemic that does not become endemic, an epidemic that comes to an end at a certain point, the final size is the total number of people that had the disease, which is after everything after the end of the epidemic, it's just R. And if you say epidemic usually has this tail here that just actually mathematically doesn't go to zero exactly. Okay? It's R, the number of recovered people at time infinity. Right? So this is not difficult to calculate. And so in order to inspect this, you take this equation here. So for the horror of people that are more formal, I just divide this equation by this equation and cancel the dt's, which will give you ds dr is equal to minus beta. You'd have si over n, which is divided by mu, and by I. So this goes away, okay? Which is just minus R0 S over N. Okay? Which can be solved. It's a linear equation for S in terms of R. So the dependency of S on R is trivial. It is just a linear equation for S. Okay? So this will give you S of R divided by N will be equal to a constant times e to minus R0 S over N. Oh, S over N times R. Okay? Pay attention. R0 is the reproductive number. This is the number of recovered. But at time infinity, this means that S will be denoted by S infinity, I is 0, and R is R infinity. Therefore, S infinity plus R infinity is equal to N. And this means that we have an equation that, that is here, S over N is the same as 1 minus R0, R infinity, sorry. Okay? So 1 minus R infinity over N is equal to e to minus R0 times R infinity over N. So, what is this? There's an equation, but not a differential equation. It is a transcendental equation that you can solve numerically or graphically for R0, for R infinity, for the total size of the epidemic. And therefore, the total size of the epidemic in this model depends only on R naught, nothing else. So this is one of the things that are important about R naught. When you have, when you calculate R naught at the beginning of the epidemic, and through a model you could estimate how many infections you would have at the end of the epidemic. And that's also what Joshua mentioned. But we have to be very careful with this. Okay, so this gives you the worst case scenario. Okay, nobody does anything. You write a model, and actually this kind of equation is true for many of the epidemic models. Even with more compartments, you still have a transcendental equation that determines R infinity in terms of R naught. So R naught can be usually calculated at the very beginning, but and therefore you get R infinity. But this estimate is an estimate where you have an infection, and the fact that you have the infection does not have any effect on the behavior of the population. This is, let's say, the people don't care, okay? Which is what didn't happen with COVID, actually, because people got, mainly in 2020, people got afraid that governments somehow acted with some policies, not always the best ones, but some. And therefore, you decrease the transmission, and in order to at least slow down the epidemic, right? And all of this is not in a model, okay? Then you could ask that you could try, and that would be definitely one thing that would be interesting, to write down models which have behavioral changes due to the fact that you have the diseases, and this obviously will modify the whole dynamics of the model, right? But anyhow, that's the final size of the equation for the final size of the epidemic, which we obtained without ever solving the SIR model. That's the same story as with R0 as with R infinity. It is obtained just by a qualitative analysis. Okay? So actually, then you could here make a plot of R infinity in terms of the reproductive number, and you have one here. If the reproductive number is smaller than 1, then obviously you don't have any epidemic, and this is something that does this, okay? And it decreases very quickly, okay? That this is here goes to almost the population size very quickly, okay? So, okay. Now, before we talk a little bit about the solutions to the SIR model, one aspect of this discussion here, which can be useful, is you write down R0, R0, sorry, and which in this case resulted as beta over gamma. Okay. So, and you want R0 to be smaller than 1. Or if you are in an ongoing epidemic, you have RT instead of R0. But you want it to be smaller than 1, which means that you will be in a declining situation of the epidemic. So knowing that R naught is equal to beta over mu, what are ideas that you could come up and how to reduce R0, R naught? How would you reduce this? Therefore, you want to reduce beta, or you want to increase mu? How would you decrease R0? Yeah, so restrict the number of contacts, okay? How do you do this in general? So you could, yeah, you could have quarantine, which is, it has effects of every, what is quarantine? I mean, the classical quarantine is you have a situation in a place and you have people incoming and the people who have to be in quarantine for some time. That was used in China with COVID-19. And this is actually restricts it's not the same as restricting the contacts in general. It's just small portion of the population doesn't have contacts, okay? And yeah, and that's it. But other ways, So you can, the beta, I mean, using masks will affect, okay, the gamma here, okay, but this gamma, okay, but this gamma, yes. Okay, so, yeah, using masks makes the probability of a contact to be smaller, okay? That's for respiratory things, okay? And the word is not only respiratory diseases. Vaccination, yeah, sure, vaccination for sure. So vaccination, it's what we have already discussed a little bit. We have the threshold and so on. That's the classic. Okay, so to be prepared. But you could have, for some new pathogen, you don't have the vaccine. Then you still have another things that you can do is to reduce the time of infectiousness. How? So if the disease is treatable, you treat the people. If it's not treatable, you isolate the person. So a person that's isolated, we don't have an isolated compartment, but we could do, if a person is infected, could be in isolated or not isolated. It could do a model with this. Right? But obviously, just isolating is a way of diminishing the time the person is infectious, effectively infectious, from the point of view of the population, not himself. Yeah, so this gives you already some insight of why RNF can be interesting, because when you have an expression for it, you can think about public health measures that would lower the value of RNF. So, solutions of the SIR model are usually made computationally. I won't repeat what Joshua already showed us, which is the phase plane solutions, and then he also showed us that the S is always decreasing function of time, R can only increase, and I has a peak, right, in this simple thing. So instead of this, let me write a new model, and which is essentially the same as IR model, but with a new effect, which is called the demographic effect. Demography, in this case, means the following. We have a constant population. Okay? Have a constant population. But there are people that are dying and people that are giving birth. So you have newborns and you have diseased people. And they somehow get in equilibrium, and we will suppose that equilibrium is perfect. And this model would be like what? You have this here is minus beta sin. Then we will suppose that there is a death rate which is independent of the person being susceptible, infected, or removed, in the sense that that's a natural death rate. We are not studying virulence. Virulence is the fatalities which are induced by the disease. So S has a death rate, which will be some nu times S, and I will have essentially the same thing. And R is plus now the individuals that are born. Okay? But we want the population to have constant population. People dying, people giving birth. They have to come to an equilibrium. If you sum up this here, d dt S plus I plus R, this cancels with this cancels with this, then you have equal to minus mu times S times I times R. Sorry, there was a mistake here. S plus I plus R plus, let's call it B, people that are born. Okay? So what do you need to do in order to have a 0 here? Well, this is n. You want it to be constant. So here you have just to put nu times n. And this makes the equilibrium, and you get a constant population. So this is a population which has the demographic effect. And what will be the effect of this demographic effect? The effect will be, first, it is not difficult to calculate R0. Okay? R0 is always calculated in this kind of models where we have only one infective state. Looking at this equation here, okay? And then seeing when this is bigger than 0, and at the beginning, then you make the same argument here that S is close to n, and then you have I times mu plus mu. So the R0, by the same reasoning we had before, will be just beta over mu plus mu. Right? Because they appear here, and that's the only equation that you are using. So you have both of them multiplied by I. So this is R0, okay? So, but now, the point is, if you look through these equations, both models here, you can ask yourself, what are the fixed points of this model? A fixed point is a point. If you know dynamical systems, you know this. But if you don't, it's just the values of S, I, or R, such that the right-hand side is 0, and therefore you are at a static equilibrium. Okay, nothing changes. If you do this for this case, there's always one equilibrium, which is I equal to 0. Okay? Here, I equal to 0, and S can be anything. Okay? Because you have 0, 0, 0, 0, 0. Okay? Here I also have I equal to 0, which is obvious to be an equilibrium. But this means that there is no infection. Therefore, there are susceptibles, infected and removed, will be constants because there's no dynamic of infections. Okay? But this here also has a fixed point, which is non-trivial. So if you do this, if you put this equal to 0 here, you can calculate the values of I, R, and S such that this side here is 0. Therefore, S, I, and R will be constants. Okay? And you can do this. And it's a little bit only of algebra. And I will say that I will put a little star here to say that this the equilibrium value of the number of susceptibles will be like this. And the number of infected in equilibrium will be something which will be nu over beta R0 minus 1. And the R has also an expression. It's a little bit bigger expression. I'm not interested in that. But what is interesting here is that this system has a fixed point, which is non-trivial in the sense that there are a certain number of susceptible, a certain number of infected people all the time. Therefore, there is the possibility that the infection, the disease, the epidemic, does not burn out completely. It goes to a fixed point, which means that you will always have infected people, which we call an endemic state. So instead of having a curve like that one here, which goes to 0 at the end of the epidemic, there is no end of the epidemic. It goes to a certain constant. Now, for those of you who have studied dynamical systems, you know that when you have a fixed point, you need to know the stability of the fixed point. Okay? So the stability of the fixed point can be studied by linearization of the equations and so on. If you never heard about this, it's not so important, okay? If you heard about it, it's trivial. So, but the important thing is you will, at the end, make a linearization of the equation, and you will look at the eigenvalues of something. And it will turn out that this fixed point here is always stable if R naught is bigger than 1. Okay? So if there is an epidemic, there will be a stable state, which is endemic in this model. But how do you approach this state? That's the point, because you will start with a certain number, small number of infections, and then S will decrease and so on. But you could go directly to the fixed point, or you could go and oscillate, and after oscillation go to the fixed point. And that's actually what happens. And mathematically, it comes from the fact that when you look for the eigenvalue of the Jacobian of these equations, it is a complex value of always showing always stability of the equilibrium, but on an oscillatory way, which will give you an equation, a solution, which is something like this. You start with a small number, you oscillate, and go to some fixed value here. Okay? So what is this? These are recurrent epidemics, if you want. But it's a periodic. It's not a periodic solution in the sense that it doesn't repeat itself because the amplitude is not constant, but it's an oscillating solution. And this is the case where you have initially a big epidemic, and then you have repeatedly new epidemics. This is generated by the fact that you have new susceptibles here. Here's an income of susceptibles, and when they build up at a sufficient large number, you can go from a decreasing situation for I to start again a new increase of S, of I. Sorry. And this is not the only mechanisms for endemicity in this kind of models. It is one other way of looking of having this endemic state is you have here, say in this case, if your immunity is not perfect, or meaning that the immunity is waning, and waning immunity would make people that are in the R class go back to the S class. Okay, you might have something minus, let's W R, which could go to plus WR here, for instance. Okay, and this would have a similar effect. Okay, of generating an endemic equilibrium and recurrent epidemics. Right? And going to an endemicity state. Okay? So, that's almost everything I have to say. The only thing that I would also like to mention is that for COVID-19, most of the models are much more complicated than this ones. The first thing is usually you have an exposed class. So instead of having S, you go to exposed, goes to infective, goes to R. And exposed is a person that has been exposed, but is not infective at this point. Then you could also have a different cases when you have people that have been exposed and they go through an asymptomatic phase, which would be a new compartment, where they can transmit, and that was what Joshua was telling us about how dangerous this is kind of thing, because the people that are not they are not ill, but they transmit. Yeah? But this kind of model where E is just exposed seems to be like, okay, why are you putting this E there? Because the guy is effectively he's not any more susceptible, but he's not infective. Okay. What's the effect of this? The effect of this will be that if you compare this model to a model without this class, the initial increase in this model is much slower than in the SIR classic model. Okay? So you have a slower, because it's kind of slowing down. You have the people in the class E, and then you will have, depend on how long people stay in this class and so on. Okay? But, well, now, what would be the classes that I have to introduce for instance, COVID-19? If you want to introduce for COVID-19 something more realistic, there are lots of things that you have still to do. The first is you have to have a death rate. Right? Okay? So that's the initial thing. But then it depends on the structure of your data. If your data is like the Brazilian data, which is number of admissions at the hospital, then you need to have a compartment which is not only I, but would be these guys which are in hospital and these guys which are not in hospital. Okay? Then they would have different parameters. Okay? The persons that are in hospital probably, so they get some kind of isolation. Okay? They have a higher death rate, but they have also a smaller contact rate. And then you have people that are not in the hospital, and 2 minutes. And people that are not in the hospital will get more contacts with a lower death rate. Okay? And then you could also introduce quarantine and so on, so on. Okay, so that's all for today. If you have questions or comments, you're welcome. Yeah. Mm-hmm. It is attraction, yeah. It's a spiral. It will be something like this. It spirals towards a fixed point. It's a spiral. More questions, comments? Right? No? Okay. So that's it. Thank you.